Okay, let's go ahead and we'll get ourselves going again so we can get a little bit done and still get you out on time and still have some time to answer some questions. So we are going to continue with this story. We have this mass floor schedule. We're tallying things up. We have some different shapes over there. Things are looking pretty good. Now, if all we were going to do was go through and kind of create rectangular boxes, again, this wouldn't be nearly as interesting. You can go ahead and actually make these boxes a little more interesting, though. For example, if I take that form, that little form that all the floors are stretching around inside, and you edit it, you can start doing things that are a little more interesting. For example, I can grab an edge and pull the edge out. Okay, and make it, kind of like a self-shading building. And we can think about whether that's going to have a good effect on the energy or not. Okay, notice as I do that, the floors all adapt. Now the floors are all uneven, so it's a little more interesting about why that schedule is valuable to us. But you can go through and compute that, and everything's kind of looking okay. So we can just start reshaping things. We can sort of push that up. At the same time, we could go through and edit this. And I want to push that one down, I can. I can make some building that really has quite an odd shape like that. Okay, let me undo that. That's a little odd. I don't mind the self-shading building. That's actually a pretty good strategy for doing some things. We can also start adding to our building. So for example, this building right now is sort of a single block. If we wanted to sort of have an L or sort of an extension to it, I could draw some more forms. So for example, I could go through and I could draw this either on level 1 or I can extrude it out from the side of the building. Really, whatever way. It doesn't really matter which way. Just anything that you enclose as a form will ultimately be divided into floors. So for example, I can, let me go ahead and draw another little extension to the building over here. Now, this is just a profile so far, so I need to do the same thing in terms of creating a form. Okay, now I have these two little sections of the building. If I finish the mass there, you'll see the floors extend out into it. But now I can go ahead and stretch that one out if I want to. Okay. Or I can decide, what I would really like to try on something like this is, I got this long squatty building. What if instead I went for the strategy where really that was kind of a tall tower? Looks like I only have 10 floors though, so that's why it's stopping right there. I can add some more floors and start to extend it that way. So you can really have this ability to kind of very quickly push and pull and twist and try different options. And that's really nice. So I can add things together. Other things, let me edit that in place. It doesn't just have to be sort of these very rectangular forms and extrusions. I could go through and do circular forms or something like that if I want to put something here at the end. I'll make a form out of that. Now, notice for this one, a circle actually has the option. You might have meant a sphere, you might have meant a cylinder. So it asks you that, which one you have in mind. I'm going to go for the cylinder. I can pull that up. Or if I wanted to, I could have made that a void instead. So if I can grab the form. There it is. Let me make it a void as opposed to a solid. And with any luck, it'll cut it out. So we can play all sorts of games, but if you can sort of imagine being in a helicopter hovering over Las Vegas, like this is the way a lot of buildings get designed, is really at this level. They don't really sort of start at the small level. People really think about it at a very high level, and then we kind of narrow on down and sort of start subdividing that space and kind of figure out what the total impact of that's going to be. Okay, so a lot of playing around you can do with these forms. These forms just let you know, can also be very imaginative. So I'm going to create another mass, put it next to it. So these are all kind of based on kind of relatively simple shapes. If, for example, I wanted to do something like this, let me zoom on out. I'm going to go through and, again, put some ellipse out here. I always like ellipses because ellipses are just sort of hard shapes. And I come over to level 3. Actually, maybe we'll do it in 3D. It'll be easier to sort of see it over there. I'll go to the top. Okay, there's the ellipse on level 1. Let me draw another level ellipse. I'll put this one on level 5. Yeah, 3. Yeah, 4. I can't make up my mind. Okay, and maybe up on level 10, I'll put something else in there entirely. I'll put like some sort of funny just sphere or circle up there. Okay. Kind of looks a little odd, but if I grab those 3 things, I do it this way, I'll get them all that way. Say create a form out of those things. It does what's called a loft between them. Okay. Looks a little strange, but I can then take that and apply the mass floors. Say okay to that. Okay, and now we have all the floors computed for that building too. So just want to give you the sense that this is really incredibly freeing. You have an awful lot of control for doing whatever you want to in terms of being able to model almost any shape that you want. And then what we're going to learn next time is how we can take these shapes and actually use that shape to generate true floors, put a skin on the building, put things like the structural elements inside of it, put a shaft in there and stuff like that. But often you can start by just sort of experimenting with forms and get a building out of that. Okay, so that's half the lesson. We're going to go through do that part next time. But what I want to continue with this time, just so you can see, is the whole notion of really, okay, we've got these shapes, they're interesting forms. I've sort of achieved my architectural objective of kind of making something about the right size. Actually, it's a little bit big right now since I have the 2 buildings there, but I'll let that be for now. Okay, I might want to think about really what's going to be the most efficient shape from an energy standpoint. And, let's kind of see how you can get some quick feedback about something like that. I'm just going to put that away for a second. Take a look at this. So I got this big old form. It's kind of hanging around. It sort of looks like floor plates, but it doesn't really look very much like a building just yet. If I want to start thinking about really how much energy a building of this shape might consume, there actually is something called conceptual energy modeling, which will give you a really quick answer to that. And here's how it works. You can go to the Analyze tab, and there's a whole series of different energy analysis tools. In these energy analysis tools, the first big choice you have to make is really, are you going to be modeling the energy based on the form or by the actual building elements? In this case, we don't have true building elements here. We're going to do it just based on this conceptual mass. So a very simple model of the surfaces and the surface qualities, we'll use that to go through and do the analysis. So there's this first choice right here, like are you going to do it with a conceptual mass, you can do it with the building elements. We'll start with conceptual masses later on when we put a skin on the building and we have true windows and walls. We'll switch over and use the building elements as opposed to just the mass. But even at the mass level, we can say that all these different surfaces transmit a certain amount of heat, a certain amount of energy flows through them, and kind of do some estimates around that. Okay. Let me go ahead and do something called enabling the energy model. Show you what it does real quickly. So what it just did was, based on that form, it went through and actually created something that actually looks somewhat like a building. Actually looks like a building in a lot of places in the country. For each of those different floor levels, it's gone through and kind of divided up the building. It sort of put some walls, some solid wall. It's put some glazing in there and some sort of a ratio between the two. It looks like it's actually tried to create a building out of this just by clicking a button. And this building, well, it's not the most refined building,
in terms of necessarily having all the surfaces articulated just the way you're going to want to in your finished design, it's probably pretty good for at least getting some really quick answers about how much energy this thing's going to consume. So, and that's really what we're after now. This is going to be the finished design. We just want to get some really quick ideas so we can figure out, do we want a tall tower? Do we want something flat? What's the effect of the ratio of the glazing to the walls? All those things. So I'm going to go back and take a look at how we control those things. There's actually a dialog called Energy Settings. Let me just kind of walk you through it. And we'll sort of see what we can change. So we are in Oslo, Norway, as our crowd suggested. Okay. We have a building type called an office. And what does that actually do for us? There are a lot of different types in here. But the type of building, you'll see everything from museums to penitentiaries, to religious buildings, to schools, to sports arenas. There's all these choices in there. Each of those different choices has some assumptions built into how many people are actually in that space, what the density of people in that space is, and what the operating hours of the building are. So for example, single-family homes, they're relatively not so dense. You have a small number of people occupying a whole lot of square footage. Okay, and they're typically not there 24/7. There's sort of a usage pattern when we use more energy and when we don't use so much energy. Offices, okay, they tend to be 5 days a week, 8 to 5. They have higher like that Saturday and Sundays. Maybe not so much energy use. Maybe not at midnight and 1 in the morning so much. If I went to multifamily homes or arenas or sports arenas, it's different. Sports arenas, often they're sitting there empty, but every once in a while there's 100,000 people in there. Okay, so they have these very kind of spiky loads. So the use just the building type says something about what the likely use is going to be. I'll just leave it at office for now. Okay. In terms of how we're computing things in the model, we'll leave that alone for right now. What I want you to think about is really some of the big ones in here are just this notion of really what the glazing percentage is. You see right now it's set to 40%. And what's happening is on all these different wall surfaces, on average, it's taken every wall surface and said, you've got 100 square feet, I'm going to use 40 as glazing and 60 as solid wall. So it's just making a really rough assumption. You can change that. We can change it to 20 or 30 or 60 or 80. We'll do that in just a second. Well, I'm going to do it right now. Let's say they were 80% glazed. Okay, and it's a very glassy building now. If I change it on the other hand and say, it's only going to be 20% glazed. See, it's not so glassy. In terms of what's going on. And we don't have to do this kind of on the entire building. You can actually just choose pieces of the building. For example, let's see if I can get to them. Now, what do I have to do? I want to do some tabbing. Okay. I got all those. That's just the type of glass in there. Hang on. I'm trying to get the wall sections in there. Tab, tab. That's the surface. That's it. By surface, I can take that and say, for this one area, go ahead and just make it 80% in that one area. So that's kind of a glassy surface within a primarily kind of relatively solid building. So I can go and start adjusting those things. Now I'm going to encourage you not to worry about getting too refined at this level. Just we're going to go through and we're going to compute some numbers here. And these numbers are going to say that it's going to use a certain number of millions of dollars worth of energy over the next 30 years. And the actual likelihood of that being the true number, it's more likely you're going to get hit by a comet walking home tonight or something like that than that number actually being accurate. There's a lot of assumptions in it. Okay, it's not going to be the absolute number. But it's a good comparative number. So if we take all the same slightly flawed assumptions for one building design and all the same exactly slightly flawed assumptions for another building design, I can tell you which one's at least better. It's not actually producing an absolute number. And that's all we're really after here is it's a notion of better. Okay, what's comparatively better? Okay, so let's go back to this analyze. we'll say, let's go ahead and look at those energy settings. If I can stop dragging them around. I'm going to switch it back to that 40% building. There's some other assumptions here that you might want to play with, or that we'll learn to play with. One is this notion of, is the building divided into something called perimeter zones? Just so you know what's happening with that, this is perimeter zones and core offset. In most buildings, if you have interior walls, up to a certain distance away from the windows is really more controlled by the window surfaces. Within a core, though, it tends to be more constant temperature. So like in this building, all the professors' offices are like, 10 or 11 feet in, and then you hit that interior hallway wall. Okay, so their offices are controlled by the outside. The interior is not really controlled by the outside nearly as much. So the core is really this notion of, do you have an outer boundary or an inner boundary? Okay, if you turn that off, if I just make that 0, for example, okay, you'll see there is no core boundary. It is just at that point like considered like a big open plan office, something like that. And that's probably fine for what we're doing. Just be consistent in your assumptions. That's all we need is consistency across your assumptions. Just okay. So we got that. We could also sort of play around with the notion of, is the glass shaded? Let me show you what that looks like. I can put some shading in there, maybe make them 3 feet deep. What that did, a little hard to see at this scale. Pull on out there. You see all these little guys? Those are light shelves, little shades on the windows. And we can put those on some sides. You might want to put those on the south side, maybe on the east and west sides, probably not on the north side. Well, unless you're in the southern hemisphere. Okay, but we can go through and like adjust those too. But again, I'm going to turn those off because I just want a nice baseline to operate from. So I'm going to say, hey, let's just take a look at a 40% glazing window in Oslo, Norway, so we can figure out really what we can say about it. So for this shape of building and this amount of square footage, let's go through and I'll run an energy simulation. Okay, when we do this, it's actually going to go and send something off to the cloud. So I'm going to call this is my Oslo sample. And I'm going to say this is my 40%. It's going to send it off and start running an energy simulation. It's going to go off and do some stuff in the cloud right now. So let's let it just go off and do that. Okay. As long as we're testing 40%, let's go ahead and try something instead. What would the effect be of, let's say, a 20% building? And we'll run an energy simulation for that. So I'm going to make that the 20% glazing option. Continue with that. Okay, we might run the 80%, just sort of see what the effect of all that glazing is. It's actually kind of interesting about just really how big an effect that can have. And I'm going to, again, go energy settings. I'll do 80% in there. Now, for this, just as we're letting it run there, for the different surfaces, there are some assumptions that are being built in there in terms of what the exterior wall and the interior wall construction is. Like, this is a mass exterior wall that's typical for a mild climate. Oslo probably doesn't qualify there, so this will probably be a fairly leaky building in that the R values, the resistance values in the walls probably isn't as high as it should be, but the analysis will actually sort of tell us that. We can ratchet this up and sort of see what the effect of a relatively lightly insulated building versus a kind of very highly insulated building could be. We can really go through and change those. And at a high level, these are just sort of encoded with different R values. We can look and help and actually see what they are. But, well, let's just do it. We'll do the, let me do the 80. Let me run that one, and then I'll go back to 40 and put in the high insulation and see what the effect of that is. Okay, so I'm going to run this 80% glazing building. And then finally, I'm going to switch back to 40% and see what the effect of, 40% is already ready. Let's send that one off. So I'll change this over to, let's say a 40% glazing again, but let's go ahead and make that a really nice, heavy-duty, high insulation sort of building, as opposed to a mild climate building. Okay, won't look any different in the picture, okay, but it's going to use some different values. So again, I'll say 40% high insulation. So we can play with all these different things. The glazing percentage, we can play with the amount of insulation in the walls. We can also start playing with the shapes. And really, if you think about it, for any sort of building of a set area, let's say we really had to come up with 400,000 square feet. We come up with that a number of different ways. I could come up with a building which is very flat. Very big, but very flat. Maybe it's only 2 or 3 stories tall. Okay. I could say, no, I want it as an other extreme, say, I want 400,000, but instead of being a very flat building, I want a very tall tower. Okay. As a third alternative, I could say, I want 400,000, but I'm going to go for a building which is relatively cubic. Okay, so if I had dimensions so that all 3 of these buildings all delivered 400,000 square feet, okay? What does your intuition tell you about what's actually the most efficient shape? Okay, so let's think about each of the buildings. What really drives it? What really, if really the whole notion of energy flowing in and out of the buildings is all about the surfaces and what the qualities of the surfaces are, so what's the most efficient shape?
I was going to say what affects it and how much is exposed.
Yeah. It generally has to do with how much is exposed, okay? How much surface area is exposed. So what tends to happen, if you were really a mathematical type, you'd say, okay, well, what's the maximum amount of volume I can enclose for the minimum surface area? Okay, and what shape is that? What volume will enclose the most amount of volume? Yeah, it's a sphere. Okay, so spheres are actually pretty good shapes, and if you sort of follow that principle, this cubic building, it's not exactly a sphere, but it's getting closer to that. This is probably enclosing the most amount of space with the least amount of surface area, is a building that's something like that. And if we were sitting there in space, this would be absolutely true. That would be how we would actually sort of go. Okay, if this was out just floating in space, and it was exposed on all sides, that would definitely be the winner. I guarantee you that. Okay. We aren't in space, though. We have this funny thing called the Earth we sit on top of. And the cool thing about the Earth relative to energy performance is it's relatively inert. It's a pretty good insulator. It doesn't really heat things up too bad. It doesn't really cool things down too bad. It's actually about the best insulator there is. So what happens is you could almost subtract off the effect of anything that's directly accounted or directly in touch with the Earth, because you're not going to lose a lot of energy. You're not going to gain a lot of energy through that. Okay. So given that, okay, let's think about these 2 different buildings. Okay, my tall, skinny tower. How do you think this one rates in terms of amount of exposed surface area relative to the amount of area enclosed or square footage area enclosed inside there? Yeah, is this a very efficient shape? No, this is actually one of the worst shapes in terms of strictly energy efficiency. So you might say, well, why do we build all these tall towers in cities? Stuff like that. Okay, and the answer is, well, if we really think about sustainability, how much land we're consuming, how much land is available, there's a lot of reasons we do build tall, very compact cities and stuff like that. So as we're talking about sustainability, just the energy use itself is not everything. It's just like one small piece of the total equation. So we're talking about energy use because we can compute that, but don't make the mistake of assuming that's the entire story, because there's all these other factors in there, and there's a lot of places in the world where we have to build tall towers because we have to have an awful lot of people housed very, very efficiently, and we need to go ahead and build up and have vertical cities as opposed to flat cities. Okay. This kind of building, this really long, low, only 2 or 3 stories tall, kind of really hugs the ground. How do you think that one rates? It turns out it's often not too bad in the scheme. Your winner will almost always be somewhere in there. It'll be one of those two. It'll be something that's relatively low. And the only reason this sort of wins, it's not necessarily the most efficient shape. What happens is all this area down at the bottom is considered relatively inert. It's not losing any energy. It's not gaining any energy through it. So these long, low buildings often win. Okay, so when you think about when Amazon's building some giant server farm or something like that, you know, we build these gigantic warehouses, and if you have a lot of land available, that turns out to be a fairly energy efficient shape. Okay, so but they have another issue because they have a lot of heat to displace, you know, something else going on. But you know, there is something about the shape of the building that actually does have an impact. So just kind of file that away. Let's go ahead and take a look at what these results are telling us and see what they have to say. So I'm going to go to some results, I'm hoping. There we go. Looks like some of the buildings are done. Maybe some are they still running? Let's see what's going on here. So here is my 40, well, let's go to 40% glazing first. That was the first one we ran, default assumptions. We're hanging out in Oslo. We know that this currently has about 1 million square feet because I'm overly sized right now. I have the 40% ratio. This building could theoretically hold about 3,700 people. That's a lot of people in there. They have an electricity cost and a fuel cost. These actually come out of a database for Oslo. So someone actually keeps track of all this stuff and knows how much electricity and fuel costs in different parts of the world. That's coming out of the server. There's a notion of something called the energy use intensity. And that's a really good measure for understanding buildings at a high level. What it does is it takes the total amount of energy that's going to be consumed per year and divides it through by the square footage. Okay, and that actually turns out to be a pretty good measure for comparing buildings because I can compare my small building to your big building. It won't really, if I just looked at the total energy, I'd have to actually care about the fact that my square footage and your square footage are different. So as an average, energy use intensity is a pretty good way of looking at it. You can start seeing how much fuel we're using, typically for heating, how much electricity we're using, often for cooling and lighting and plug loads and all those different things. Okay? You also have this notion of really how much we think it's going to cost over 30 years to go through and heat and cool this building. So about $10 million here. Over a 30-year lifespan using 6.1% discounting. So if you're in the engineering economy and you're playing the whole game of the time value of money, it's actually more, but we're discounting the money because the 30-year out money isn't worth as much to me as the money that I'm spending today. Okay, now we can go ahead and try to drive that down. Anything we try to do to drive that down, we have to offset by the increased cost of whatever we're doing to try and drive it and make some sort of value judgment. It's giving you some sense of the amount of photovoltaic potential, how much we can actually generate through photovoltaic power or sort of wind turbine. You'll see that, well, this one doesn't actually have very much energy use potential. It's kind of interesting. In the scheme of things, it's thinking, I think it's because we're so high up in Oslo, Norway, the amount of sun we're getting is really not going to be very promising in terms of doing photovoltaics. Okay, so it has some calculations going on in the background that are assuming that. We can look at really how much, where the energy is going and look at a lot of different things in here. We're going to take a look at this. Oh, yes? We can say that in terms of the heating load, in this chart we can see a little bit about, well, what's going on here? Window, if I look at all the different places we're losing heat right now, probably the biggest thing is this notion of window conductive. That's how much actual energy is actually going right through the window surface. So if I was looking at improving this building, I might take a look at just improving the efficiency of the windows. Something that has a lower U value. So it's something that's not conducting as much heat. What would be next? Most of the rest of it's not too awfully bad. Lighting fixtures. Walls and roofs, you can see compared to the windows versus walls and roofs, Roofs is especially not bad at all. Walls is that's infiltration. So walls is out here. In the scheme of things, if I had to focus anywhere, I'd focus on the windows as opposed to focusing on the walls and roofs. Looks like they're pretty well insulated already. On the cooling side down here, you can start to see that, oh, what's going on with my cooling? Of all these different areas, the equipment's generating a lot of cooling load, the lighting fixtures are generating a lot of cooling load. Windows solar is generating a fair amount of cooling load. So during these summer months, it might be worthwhile to go through and shade the windows somehow. Do something that's cutting down on the amount of solar radiation that's coming through there, so that will just keep the air conditioning a little bit less. So that's what it's kind of predicting at a high level. But the important point here is it's not so much this notion at a high or precisely what the numbers are, it's comparing things. So let me just kind of compare some different things. We have the 20 versus the 40. I can grab those two and say compare them. Put them side by side. 20 is now on the left, 40 is on the right. So if I greatly cut down on the amount of glazing, you'll see that I reduced the energy use intensity some from 54 to 49. I've reduced the total cost from 10.3 to 9.6. Well, I probably actually sacrificed quite a bit of the architectural appeal of the building by kind of making it so enclosed. So I'm not sure that was necessarily worthwhile in terms of what's going on. Let me go ahead and switch it over to the 40% or the 80% glazing. We'll head in the other direction and see how that looks. If I put all that glass in, I'm going to go from 54 all the way up to 67. So again, I'm over the 30-year life, I'm spending somewhere around $2 million extra. And you can decide whether that's worthwhile or not in terms of getting all that extra sort of view out of those things. Let me try just as opposed to going down, we had 40%, we had 20%, which sort of saves some energy. Let me try 40% high insulation on the walls. Well, it looked like the walls really weren't all that bad. I probably would have been better off changing the windows. So 20% brought us down to 49. High insulation brought us to 52. 54 was with just standard insulation. So with all these things, I'm getting a little bit of feedback about where it might make the most sense to spend our time in terms of making some improvements. Actually, given this feedback, I'd probably go back to the windows and change the window properties. Yes?
So is this meant to replace eQuest, or is this something you would do before you put it in?
It's before eQuest. This is sort of really quick. The idea here is go through and just come up with some very quick models in 10 minutes, throw some stuff at it, get some quick guidance. You can then export this model, take it over to eQuest, and do a much more detailed analysis. So it's really just, it's that little pre-step before you get to that. So if I wanted to go through and try changing something about the windows now, or the window efficiency, I could say, let's go look at those conceptual assumptions. And as opposed to just sort of the standard windows, where's the glazing? There it is, double pane windows. I can say, what would happen if they were actually, triple pane windows, or just had some low E, low solar heat gain coefficient in there for a cold climate. So let me go for like a double pane clear. This is sort of a better, still a double pane window, but just sort of a better qualities for a cold climate. Say okay there. Let me run that energy simulation. We can go through and compare that. Low E windows. So we can do something like that. At the same time, we can go through and just change the shape of the building. We can reorient the building. All those sorts of different things we can start playing with to just try and get some quick answers. And that's really the point of this, is really just experiment with different shapes, get a little bit of feedback around what the energy costs are going to be associated with that. And out of that, try and figure out, just really what shape of building you ultimately want to have. So for example, right now, I guess that's the south side over here, the ratcheted side over here. If I wanted to try something like, just orbiting this around, I could rotate the building and rerun the energy analysis that way to try different orientation. I could say, you know, this was kind of interesting in terms of what's going on here. You know, what if it was, instead of being this shape of building, like a very squatty building or something like that? So I'm just going to squat this out. Oh no! Undo that. Okay, in terms of what's going on there, let's take that one there. Again, I'll flatten that out. So just much lesser. And now we can go through and do that same notion of, let's just run that. Okay, so analyze. We'll call it the low flat building. Okay, going back to the energy simulation results, let's take a look at those for just a second. Let that finish sending it off. For my low E windows here, 40%. What we were comparing to 54 or something like that. Looks like that brought it down to 50. So actually, it was, I believe, was it more efficient to actually change the Windows 20 versus low E windows over here? Let's compare those two. 49 versus 50, something like that. So really relatively little difference. So just by using a slightly better grade of window, I can go through and pretty much achieve the same as actually cutting out half the glass in the building, or something like that, and achieve a very similar sort of cost. So let's just go ahead and put this into perspective in terms of what it all is. What's this all about? At a high level, we're really just trying to say experiment with different forms, try and figure out what you think the good shape for your building is going to be, and as you're evaluating the different shapes, considering energy use as one of the different factors that you throw in there, as well as all the architectural features that you want to put in there. Oh, looks like my flat building's ready now too. Let's take a look at it. That has an energy use intensity of 45. So there's that funny thing where the low squatty buildings often sort of win, just because they're so underground. They're so exposed to that they often have a very high or a very efficient shape to them. Okay. So let's go ahead and leave it there for tonight. Where we are going to go with this is, we on Thursday are going to say, okay, it's great to go ahead and have these shapes. We're sort of understanding our buildings this way. This is looking pretty good. Let me go ahead and put that back in here. We'll say show mass floors and forms. This is looking pretty nice, but this doesn't look very much like a building just yet. So what we're going to learn how to do on Thursday is as follows. We're going to take that fantastic shape there that looks pretty good. We're going to say, I would like to actually turn those mass floors into real floors. So I can start actually converting them into floors. And that top of the building over there, I'd actually let that be a roof. And we can choose some sort of roof surface to it. Then for the walls of the building, I could say, I kind of like those walls. I'll put some solid walls on. Maybe this side. Maybe the back side over here. But I'm also a big fan of curtain systems. So maybe I'll orbit that around. I'm centered in a funny place. So if I would like a curtain system on those, I could choose, for example, curtain system, and choose that surface, and maybe I'll control click and get that surface there. And I'll just make a curtain system. Remember those curtain systems with the standard panel sizes? Okay, so what's happening is started as a conceptual mass, did the energy analysis of conceptual mass, but like in the last 3 minutes, we just went from a conceptual mass to actually a building with walls, floor, roofs, curtain walls, all that type of stuff. We're ready to go ahead and put a staircase in this now, or something like that. And that's the idea of how this workflow can go. We may want to keep on customizing this, we may want to keep on being much more refined about it, but if you can take those conceptual ideas and really quickly get them into real buildings, okay, it's just a very nice, smooth workflow to follow. Okay, so that's what we're doing Thursday, is how we can do that. And that's actually the same sort of thing you're going to be doing on the next assignment. We're going to give you a program, you're going to kind of consider some different shapes, come up with a shape that you like, compare a couple shapes, choose one you like, and ultimately make a building out of it. You put like a frame inside of it, and go ahead and just think about the scale of the building and how you can go and make something that achieves those program objectives. Okay, so come on back on Thursday night, and we will continue the story.